The next concept is heat capacity and specific heat capacity. So you must have learned this previously in your preliminary classes, that what is heat capacity? Heat capacity is like if you have a body, like and you're supplying some Q amount of heat inside it. So in response to this Q heat that you have supplied inside the body, the temperature of this body will increase, right? So heat capacity is nothing but the ratio of the heat supplied versus like to the amount of the delta T experienced by this body. Right? If you supplied 10 joules of heat into the body and the temperature change experienced by the body was 2 degrees, so 10 by 2, 5. So 5 joules per Kelvin or 5 joules per degree C is the same thing, will be the heat capacity of the body. Now, if you have a bigger body than this, now if you have a body which is twice the size of this, now the same amount of heat if we supply to that body will not give us a 2 degree rise in temperature. Why? Because the body has become like is bigger now, right? So if you supply the same amount of heat, the overall temperature will be like 1 degrees because the size has doubled, right? So the heat capacity is dependent on the mass or the quantity of the body, and that is why heat capacity is an extensive variable. It is dependent on the mass or the quantity of the matter, of the material, right? So in here, C, which is the heat capacity, is Q by del T. Now, simply written like for a small change in heat and corresponding to a small change in the rise in temperature, we have written it like this, like del Q by dt. The units are joule per Kelvin. It's very simple to understand, right? So this is for a bulk, this is for a small amount, right? This is how we write it. So this is heat capacity. Now, extensive variables are not easy to handle because they are like dependent on the amount of the material. So normalize the effect of the mass. What we divide is just divide the whole thing by the mass, and we call it the specific heat capacity. Now, if you have the specific heat capacity, it's the same thing, dq, del Q by dt. We just divided it by the mass of the body. Now this is denoted by a small letter c, which is called now the specific heat capacity. Now specific heat capacity, because it's normalized, is now normalized by the mass, has now become an intensive variable, which will now not depend upon the mass of the matter, right? Mass of the whole thing. The units have changed because now this is dq is joule, dt is Kelvin, and mass is kg. So this has now become joule per Kelvin per kilogram. So the specific heat capacity. Now, there are interesting things happening in specific heat capacity for gases. Now, why not solids? So, for solids, even if you have, so let's assume you have a solid and you're giving some heat into the body, and you're trying to see how much is the temperature of the body increases by how much. Now what happens is, for a solid, generally the volume or the pressure inside the volume of the solid does not change, right? So even if you have a constant volume process or a constant pressure system in which the pressure of the whole system to the outside of the surrounding is not going to change drastically, because the system remains more or less constant. It doesn't change its volume that much. So the specific heat capacity of a solid or a liquid is more or less the same, given even if it is like constant pressure system or a constant volume system. But the story of gases is entirely different. It becomes very, very interesting when you see what happens to the heat capacity when you take constant pressure systems versus constant volume systems. Okay, I'm so excited. Okay, now let's see what happens in here when you have a constant volume and versus a constant pressure, specific heat capacity. Now let's see. We have discussed this before, that if you have a subscript P, that means the pressure is constant. If you have a subscript V, the volume is constant. So Cp means that this represents the specific heat capacity of that gas or any of the solids, any material at constant pressure. Cv is the specific heat capacity of that material at constant volume. So let's assume that we have a system like this. Okay, now we have a system in which there is this piston and there is this and we are supplying heat into the system. Okay, now when you are supplying heat into the system, say you are supplying 10 joules of heat inside the system. Now I am telling that I want to keep the pressure fixed. Now when you give heat, these molecules start to get more energetic. When they get more energetic, they start to move with higher velocities. Now, because of these higher velocities, the pressure experienced, pressure exerted by this system to the outside increases. But I want to keep this pressure fixed. Now, how will you keep the pressure fixed? We have to change the volume, right? So if you change the volume, if you expand it, the pressure will almost remain the same. So we want to keep that pressure same. To keep the pressure same, we change the volume, we increase the volume, okay? Now, let's assume that we supply 10 joule of heat in here. Now, we are expanding, we are doing some work, the system is doing some work, and the system is getting more energetic, it's increasing its temperature, right? Because temperature is what? Just the average kinetic energy of the gas molecules, right? Now, this 10 joule of heat, or this 10 joule of heat is spent in two different things. First, to do some volume change, to do some work, and the rest is going to increase the temperature. Now, this is a waste if you understand, if you want to look at from this perspective. This is a waste. Why? Because you gave 10 joules of heat and you wanted to increase the temperature of the system, but not all that heat is going to increase the temperature of the system. Some of it is going to waste to do a work, to do some work, to do some volume change in here, right? To expand the volume, for expansion of this whole system. So only this 4 joule of heat, which is 10 minus 6, 4 joule of heat remains, that is available to increase the temperature of this system, right? Now, if we want to now find out what is the specific heat capacity of this gas at the constant pressure, now you had 10 joules. Now you have to take into account that you gave it 10 joules, right? But it couldn't use that 10 joules entirely to do a pressure, to increase the temperature of that system, right? So you need more heat in here so that to counteract this loss, right? To counteract this loss. So say you want 8 joules of 8 joules energy to raise the temperature, okay? Now 8 joules is not available directly. Now you have to give more and more heat to compensate for this loss, which is going to change the volume. So ultimately you are giving more Q. If you are giving more Q, then inherently Cp is increasing, right? If you are giving more heat to raise the temperature of that amount, then inherently you are increasing the Cp, because what is Cp? It's dQ by dt. To raise the same temperature, you are giving more, because more amount of heat is needed, because some of it is going to waste. Now, the story becomes different when you have a volume fixed. Now, if you fix the volume, you are telling that, okay, we are not going to change the volume of the system. That means we are not going to spend any of this energy in doing expansion, in doing work. So, all of this energy that is available through Q can go directly towards increasing the temperature of this system. So there is no waste. So all of this is going to change the temperature of this system. So all of this 10 joule is going here to raise the temperature. Now you do not require more because you already have given enough to raise the temperature of the system. For example, if 8 joules of energy is required to raise the temperature by 1 degrees, right? So in here, you know that 6 joule is going here and 4 joule is going this way. 6 joule is going to raise the volume to do some work here. Then you have to give it 20 joules, right, to increase 1 degrees, because then out of this 28 will be able to raise the temperature of this gas. So in here, the Cp becomes 20, right? In here, the Cp, the 10 joules, out of the 10 joules, nothing is going to waste, nothing is going to increase the volume, right? So all of this is going to raise the temperature of the system. So inherently, you are spending less energy in Cv, right? So Cv becomes lesser than Cp. So it takes less amount of energy, less amount of Q, heat, to raise the temperature of the system when you have a constant volume system rather than a constant pressure system, right? So this is extremely interesting because in here you are going to do some work which is going to spend your energy. I don't want that, because if I want to raise the temperature, I want to see the temperature raise. If you have for a CP system, some of it is going to waste, but in CV system, it's less amount of heat, you can raise the temperature. And that is the reason CP is always greater than CV. Okay, we'll come to a quantification of this later, but for now we have to understand why is CP greater than CV because of this. Okay, now you've seen this equation a number of times now. Okay, this is the first law of thermodynamics. D is equal to del Q minus del W. For the CV situation, now this can del W can also be written as P del V, as we saw earlier. Now for the CV case, since it's a constant volume, so what will happen to this del V? This goes to 0, right? So what is left in here? What is left is dE is equal to del Q, because this goes to 0 for the CV case. So what becomes of this thing, del Q? Why V? Because we are trying to see what happens at constant volume. So del QV becomes del E. Okay. Now keep this in mind. How the first law became simplified for the CV process. For the CP, what happens is this is not getting simplified. So P del V comes to the left side and becomes a positive. So del QP, now del QP signifies the amount of heat at constant pressures, right? So del QP becomes PdV plus dE. Now this is exactly this, P plus PV, enthalpy. So this basically is the enthalpy term. Del QP is basically the enthalpy. Okay, the delta, the DH concept in here. So dQP becomes DH. So for CP, this is the case. For CV, del QV is dE. Very simple. So it's just a simplification of the formula. Now let's try and understand what is happening here. Now let's formulate it. Now what is CP? Is the amount of heat divided by the temperature. Constant pressure. This P is just that. So this is what, right? The specific heat capacity was del Q by del T normalized by mass. So this is all normalized by mass. So like specific heats, right? So del Q by del T. So here we have del Q by del T, this P. Now what was del Q for CP? What was del Q for QP, right? So this was the del QP that we are going to use here. Right, that we are going to use here. So substituting this, what was this? PdV plus dE. This was the case, PdV plus. So this is basically the change in enthalpy. So del H by del, so CP becomes del H by del T at constant pressure. Similarly for this, the del QV, what did we get here? For del QV, we got a dE. So we just substituted here dE. So dE by del T at a constant volume is CV. So these are the two formulations for CP and CV. The specific heat capacity at constant pressure and specific heat capacity at constant volume. This is the del of E, which is the internal energy, and this is del of H, which is the enthalpy. Please recall that enthalpy was defined by this function, which is E plus PV. Okay?